Welcome to Science for Sleep. Tonight we will travel deep beneath the surface of our world, sinking through ancient layers of rock into a realm where one of Earth's greatest secrets has remained hidden for billions of years. Not the oceans we see, not the rivers and lakes we know, but a vast reservoir of water buried hundreds of miles below our feet. Water stored inside the very minerals of the mantle, in quantities that may exceed all the oceans on the surface combined. Before we begin this quiet journey into Earth's inner ocean, if you enjoy calm, gentle explorations like this, a soft like or subscribe truly helps the channel grow. Thank you. Now, as we descend together into the silent interior of the planet, we'll discover water in forms stranger than anything on the surface, bound within crystal structures and carried downward by the slow movement of tectonic plates, then released again through volcanic breath. This hidden water cycle operates on a timescale so vast that a million years becomes a single moment, shaping continents, fueling eruptions, and helping maintain the conditions that make life possible. Let us continue our descent, drifting slowly through increasing pressure and heat, into the quiet reservoirs where Earth stores the water of its deepest history, an unseen ocean that has shaped our planet from the beginning. As we descend together through these hidden layers, let yourself relax into the rhythm of geological time, where change happens so slowly that million-year periods seem like brief moments, where pressure and temperature follow gradients that stretch across hundreds of miles, and where the familiar properties of water transform into something both strange and beautiful. The water we will discover on our journey exists not as liquid flowing through underground rivers or lakes, as you might imagine, but locked within the crystal structures of minerals, bound chemically to rocks in ways that allow the solid Earth to hold more water than all the lakes and rivers and oceans and ice caps that cover the planet's surface. This hidden water has been cycling through Earth's interior for billions of years, carried down into the deep mantle by the slow, patient motion of tectonic plates, released back toward the surface through volcanic activity and mountain building. Participating in a great planetary water cycle that operates on timescales of hundreds of millions of years, and that has helped keep our planet's surface habitable throughout the long journey of geological history. Let us descend now into this quiet realm, moving slowly and peacefully through layers of increasing pressure and temperature, discovering the secret reservoirs where our planet stores the water that makes life possible, and allowing ourselves to rest in the ancient patient rhythms of the solid Earth that supports and sustains everything we know. The water beneath our feet, beneath the thin layer of soil and rock that we walk upon each day, beneath the groundwater that fills wells and feeds springs, beneath the deepest mines and the deepest drill holes that humans have created. There exists a realm of rock and mineral that extends downward for thousands of miles to Earth's core. And within this vast interior domain, our planet holds water in quantities and in forms that challenge everything we learned about water in school. When we think of Earth's water, we naturally imagine the oceans, covering 70% of the planet's surface, containing about 326 million trillion gallons of water, a volume so large that it seems to represent almost all the water Earth possesses. We might also think of the ice caps at the poles and the glaciers on mountains, holding enough frozen water that if they melted, the sea level would rise by hundreds of feet and drown most coastal cities. We might remember the rivers and lakes and underground aquifers that provide fresh water for drinking and farming, and we might consider the water vapor in the atmosphere that forms clouds and falls as rain and snow. All of these familiar reservoirs of water, everything visible on Earth's surface and everything accessible in the shallow crust, together contain less water than exists hidden in the deep interior of the planet, locked within minerals in the mantle and transition zone hundreds of miles below the surface. This deep water is not liquid, not flowing freely through pores and cracks. but is instead incorporated into the crystal structures of minerals, chemically bound as hydroxyl groups attached to silicon and oxygen frameworks, holding perhaps 1 or 2 or 3% water by weight in minerals that make up the vast bulk of Earth's interior. 1 or 2% sounds like a small amount until you realize that the volume of rock in Earth's mantle is so enormous that even these small percentages add up to oceans worth of water. And when you account for all the water held in transition zone minerals that can contain much higher percentages, the total amount of water in Earth's interior may equal or exceed the amount in all the surface oceans. The discovery that Earth's interior contains so much water came as a surprise to geologists and revolutionized our understanding of how the planet works, revealing that Earth is not a dry, rocky body with a thin veneer of surface water, but is instead thoroughly hydrated throughout much of its interior, with water playing crucial roles in mantle dynamics, in plate tectonics, in volcanic activity, and in the long-term habitability of the surface. How rocks hold water. To understand how solid rock can contain water, we must first shift our thinking away from the familiar idea of water as a liquid flowing through spaces between solid grains, and instead imagine water being incorporated directly into the atomic structure of minerals themselves, becoming part of the solid crystalline framework rather than existing as a separate fluid phase. Minerals are ordered arrangements of atoms in three-dimensional lattices, with specific positions for each type of atom and with strong chemical bonds holding everything together in patterns that repeat across millions of atomic spacings. Most minerals in Earth's interior are silicates, built from frameworks of silicon and oxygen atoms arranged in various configurations. And these silicate structures can sometimes incorporate hydrogen atoms bonded to oxygen to form hydroxyl groups, written chemically as OH, which are essentially water molecules that have lost one hydrogen atom and become integrated into the mineral structure. When a mineral contains these hydroxyl groups dispersed throughout its crystal lattice, we say the mineral is hydrous or water-bearing, even though there is no liquid water present, and even though the hydroxyl groups are firmly bound in place and cannot flow or move independently. The amount of water that a mineral can hold depends on its crystal structure and on the pressure and temperature conditions where it forms, with some minerals able to incorporate only traces of water, while others can hold substantial amounts. Olivine, one of the most abundant minerals in Earth's upper mantle, typically contains only about 1/100% water by weight. But even this tiny amount matters because olivine is so abundant that it makes up perhaps 60% of the upper mantle's volume. At greater depths where pressure increases, olivine transforms into denser mineral structures with different names like wadsleyite and ringwoodite. And these high-pressure minerals can incorporate much more water into their structures, with ringwoodite capable of holding up to 3% water by weight, making it effectively a very dilute solid solution of water in rock. The transition zone, the region of the mantle between about 250 and 400 miles depth, where these transformations occur, acts as a sponge that can soak up and store enormous quantities of water carried down from the surface by subducting tectonic plates. The journey downward water reaches the deep interior of Earth through a slow, patient process driven by plate tectonics. The gradual motion of Earth's outer shell as rigid plates move across the surface, colliding and separating and sliding past each other at rates of inches per year. Speeds imperceptible in human lifetimes, but sufficient to completely rearrange continents over hundreds of millions of years. At convergent plate boundaries where two plates collide, one plate, usually an oceanic plate made of dense basaltic rock, is forced to bend downward and sink into the mantle beneath the other plate in a process called subduction. The subducting plate carries with it the hydrated minerals that formed at the ocean floor where seawater circulated through cracks in the newly formed crust and reacted with the rock, binding water into minerals like serpentine and chlorite and amphiboly that are stable at low temperatures and pressures. As the plate descends into the mantle, It heats up from the surrounding hot rock and experiences increasing pressure from the weight of material above. And these changing conditions cause the hydrous minerals to break down and release their water. Some of this released water percolates upward through the overlying mantle wedge, lowering the melting temperature of the mantle rock and causing it to partially melt, generating the magma that rises to the surface and creates the volcanoes that characteristically form in arcs parallel to subduction zones. But not all the water is released in the shallow mantle. Some remains bound in minerals that are stable to greater depths, and some is carried deeper still as the slab continues its descent. At depths beyond about 60 miles, the subducting slab has released most of its water from low-pressure hydrous minerals, but it still contains water in minerals that remain stable at higher pressures. And this water can be transported into the transition zone and potentially even into the lower mantle depending on the temperature of the slab and the rate of subduction. Cold slabs that descend rapidly retain water to greater depths because they take longer to heat up and because lower temperatures stabilize hydrous minerals to higher pressures. The water reaching the transition zone can be stored there for hundreds of millions of years in the high-capacity minerals like wadsleyite and ringwoodite, accumulating over geological time into a hidden reservoir that may contain as much water as all the surface oceans. The transition zone reservoir, between roughly 250 miles and 410 miles beneath Earth's surface, lies a region called the transition zone, named not for any change in composition, but for the series of mineralogical phase transformations that occur there as increasing pressure causes minerals to rearrange their atomic structures into denser forms that pack more efficiently and that can sometimes accommodate more water in their crystal lattices. The transition zone represents a boundary between the upper mantle and the lower mantle, regions with different mineral assemblages and possibly different chemical compositions. And it acts as a potential storage reservoir for water being cycled through the deep earth. The upper boundary of the transition zone at about 250 miles depth marks where olivine, the dominant mineral of the upper mantle, transforms into a denser structure called wadsleyite. And this transformation creates a seismic discontinuity, a sharp change in the speed of earthquake waves that geophysicists use to map the structure of Earth's interior. Wadsleyite can hold much more water than olivine, with laboratory experiments showing that it can incorporate up to 3% water by weight under the pressure and temperature conditions of the upper transition zone. The lower boundary of the transition zone, at about 410 miles depth, marks where wadsleyite transforms into an even denser structure called ringwoodite, which can hold even more water, potentially up to 3% by weight as well. Below the transition zone at about 410 miles, ringwoodite breaks down into an assemblage of minerals, including bridgmanite and ferropericlase, that make up the lower mantle. And these lower mantle minerals have much lower water storage capacity, perhaps just a few hundredths of a percent, meaning that the transition zone acts as a bottleneck where water accumulates because it can be stored efficiently there, but cannot easily pass through into the lower mantle. The amount of water actually present in the transition zone is difficult to measure directly because we cannot sample rocks from these depths, except in rare cases where mantle plumes bring transition zone minerals to the surface preserved inside diamonds. But seismic studies that measure the speed of earthquake waves passing through the transition zone can provide indirect evidence for water content because water affects seismic velocities in predictable ways, generally slowing the waves slightly compared to dry rock. Evidence from rare diamonds. Our knowledge of water in the deep earth comes partly from computer models and laboratory experiments that recreate high-pressure conditions, but the most direct and most exciting evidence comes from tiny mineral inclusions trapped inside diamonds that formed in the deep mantle and were carried rapidly to the surface by volcanic eruptions before they could react or equilibrate with shallower conditions. Diamonds form in the mantle at depths greater than about 90 miles, where pressure is sufficient to make carbon crystallize in its densest form. And during their growth, diamonds sometimes trap tiny grains of surrounding minerals as inclusions, preserving these minerals like insects in amber and preventing them from transforming to lower pressure forms as the diamond is transported upward. Most diamonds that reach the surface come from the upper mantle and contain inclusions of common upper mantle minerals like olivine and garnet. But a small fraction of diamonds, perhaps 1%, come from much greater depths and contain inclusions of transition zone or lower mantle minerals that provide rare windows into these otherwise inaccessible regions. In 2014, scientists examining a brown diamond from Brazil discovered a tiny inclusion of ringwoodite, the high-pressure form of olivine that is stable in the lower transition zone. And analysis of this ringwoodite showed that it contained about 1.5% water by weight, providing the first direct evidence that transition zone minerals actually do hold significant water in nature and not just in laboratory experiments. This single grain of ringwoodite, smaller than the width of a human hair, proved that at least some parts of Earth's transition zone contain substantial amounts of water, supporting the hypothesis that the transition zone might hold an ocean's worth or more of water distributed through its vast volume. Other diamonds with transition zone and lower mantle inclusions have since been found and studied, revealing more about the water content and chemical composition of these deep regions. Though such diamonds remain rare and precious resources for deep Earth science, the inclusions are so small that analyzing them requires sophisticated techniques, including infrared spectroscopy that can detect the vibrational signatures of hydroxyl groups in minerals, and X-ray diffraction to determine the crystal structure and confirm that the minerals truly formed at high pressure. Each discovery of water-bearing minerals from the deep mantle adds another piece to the puzzle of Earth's internal water cycle, and helps scientists understand how water is distributed at depth and how it influences mantle dynamics and planetary evolution. Melting and water's influence. Water dissolved in minerals has profound effects on the physical properties of mantle rock, particularly on its melting behavior, because water acts as a flux that lowers the temperature at which minerals begin to melt, allowing partial melting to occur in regions of the mantle that would remain solid if they were to. Pure dry mantle rock at the pressures typical of the upper mantle beneath mid-ocean ridges begins to melt at temperatures around 2,300 degrees Fahrenheit. But the addition of even small amounts of water can lower this melting temperature by hundreds of degrees, causing rock that would otherwise be just below its melting point to start melting and producing magma. This water-induced melting is particularly important at subduction zones, where water released from the descending slab percolates upward into the overlying mantle wedge, lowering the melting temperature and causing the mantle to partially melt, even though it is not particularly hot by mantle standards. The magma generated by this water-induced melting rises buoyantly toward the surface because it is less dense than the solid rock around it. And as it rises, it may continue to melt more rock through a process called decompression melting, where decreasing pressure allows already hot rock to begin melting. The rising magma eventually reaches the base of the crust, where it may pond and cool, crystallizing to form plutonic igneous rocks. Or it may continue rising through the crust to erupt at the surface as volcanic lava and ash. The volcanoes of the Ring of Fire around the Pacific Ocean, including the Cascades in North America, the Andes in South America, and the island arcs of Japan and Indonesia, are all products of this water-induced melting at subduction zones, and they return to the surface much of the water that was carried down with the subducting plates, though not all of it, because some water is transported deeper than the region of melting, and some remains bound in minerals that do not break down at shallow depths. The feedback between water and melting creates a natural recycling system where water from the surface is carried into the mantle by subduction, participates in melting and volcanism that returns much of it to the surface, but with some fraction being transported to greater depths or retained in the mantle, gradually building up the deep reservoirs over billions of years of Earth history. Viscosity and mantle convection. Beyond its effects on melting, water also influences the viscosity or resistance to flow of mantle minerals, making hydrated rock weaker and more easily deformed than dry rock at the same temperature and pressure. And this change in rheological properties has important consequences for mantle convection and plate tectonics. The mantle is not liquid, but solid rock that flows very slowly on geological timescales through a process called solid-state creep, where crystals deform by the gradual migration of defects through their structures, allowing shape changes without melting. The rate of this solid-state flow depends strongly on temperature, with hotter rock flowing much more easily than cooler rock, but it also depends on water content, because hydrogen atoms dissolved in mineral structures create defects and weaken chemical bonds, allowing easier deformation. Laboratory experiments that deform mantle minerals at high pressure and temperature show that adding even 0.01% water by weight can reduce viscosity by a factor of 10 or more, making hydrated mantle rock flow 10 times more easily than dry rock under the same conditions. This viscosity reduction affects how the mantle convects, how plates move, and how the planet loses its internal heat. Mantle convection is the slow overturning circulation, driven by temperature differences, where hot rock rises from deep in the mantle toward the surface, cools, and sinks back down, carrying heat from the interior to the surface, where it can be radiated into space. The vigor of this convection and the pattern of upwelling and downwelling depend on the viscosity structure of the mantle. And if the transition zone contains significant water, making it weaker and less viscous than the surrounding regions, this could affect how convection operates and whether the upper and lower mantle convex separately or together as a single system. Seismic tomography, which maps variations in seismic wave speeds throughout the mantle, reveals complex three-dimensional structure with slabs of subducted lithosphere visible as fast seismic velocity anomalies extending deep into the mantle, and with hot, upwelling plumes visible as slow velocity regions rising from the deep mantle toward the surface. Understanding how water affects viscosity helps explain the observed patterns of mantle flow and helps constrain models of mantle convection and plate tectonics. The Great Planetary Water Cycle. As we drift deeper into understanding Earth's hidden water, we begin to appreciate that the water reservoirs at the surface and in the deep interior are not separate isolated systems, but are connected through a great planetary water cycle that operates on timescales of hundreds of millions of years, moving water from oceans to mantle and back again through the coupled processes of subduction, storage, melting, and volcanism. This deep water cycle complements the familiar surface water cycle, where water evaporates from oceans, falls as rain, flows through rivers back to the sea, forming a continuous circulation driven by solar energy that operates on timescales of days to years. The deep water cycle operates on vastly longer timescales, driven not by solar energy, but by Earth's internal heat. And it involves amounts of water comparable to or exceeding the surface oceans. Water begins its journey into the deep Earth at mid-ocean ridges, where new oceanic crust forms through volcanic activity, as tectonic plates pull apart and mantle rock rises and melts. The newly formed crust is hot and fractured, and cold seawater circulates through these fractures in hydrothermal systems, reacting with the basaltic rock and forming hydrous minerals like serpentine and chlorite in a process called hydrothermal alteration. This hydrated oceanic crust spreads away from the ridge as new crust forms behind it, eventually traveling thousands of miles across ocean basins over tens of millions of years before reaching a subduction zone where it bends downward and begins descending into the mantle. As the crust subducts, some of its water is released at shallow depths through the breakdown of low-temperature hydrous minerals, triggering melting and volcanism that returns water to the surface. But some water is carried deeper into the transition zone, where it can be stored for long periods. The residence time of water in the transition zone is uncertain, but may range from hundreds of millions to billions of years, depending on the rate of mantle convection and the efficiency with which transition zone water can be transported back to the surface. Eventually, water returns toward the surface through several possible pathways, including entrainment in upwelling mantle plumes that rise from the deep mantle, incorporation into normal upwelling circulation beneath mid-ocean ridges, or release during continental collision when hydrated oceanic crust is caught between converging continents and heated until its water is driven off. The history, written in water. The amount of water in Earth's interior today and the balance between water entering through subduction and water leaving through volcanism carry information about the history of Earth's water over billions of years. And scientists studying the deep water cycle are attempting to read this history and understand how the distribution of water between surface and interior has changed over geological time. Earth formed roughly 4.5 billion years ago through the accretion of rocky and metallic material in the solar nebula. And the amount of water incorporated during formation depends on the temperature in the region where Earth formed and on the availability of water-bearing minerals and ices in the material that accreted to build the planet. Current theories suggest that Earth formed mostly from relatively dry rocky material, but that water was delivered to the planet after most of the accretion was complete, brought by impacts of asteroids and comets from the outer solar system, where water ice was stable and abundant. Some of this water remained at the surface forming oceans, while some was buried by later impacts and incorporated into the mantle. And over billions of years, plate tectonics has been cycling water between these reservoirs. Early in Earth's history, when the planet was hotter and mantle convection more vigorous, the rate of subduction was probably faster than today, and the amount of volcanism and the flux of water from mantle to surface was also greater, creating a dynamic system where water was constantly being exchanged between surface and interior. Some scientists argue that Earth's surface oceans were larger in the distant past and have been gradually shrinking as water is transported into the mantle faster than it returns to the surface, while others argue that the system is approximately in steady state with inputs and outputs balanced. And still others suggest that the oceans may have grown over time as water has been gradually degassed from the interior. Resolving these competing hypotheses requires better understanding of how much water is currently in the mantle, how fast water enters through subduction, how fast it returns through volcanism and other processes, and how these rates have changed over Earth's history as the planet has cooled and as plate tectonics has evolved. Water and mantle melting. Through time, the connection between water and melting means that the amount of water in the mantle influences the volume and composition of magma generated at mid-ocean ridges and at subduction zones, and changes in mantle water content over Earth's history would have affected the production of oceanic and continental crust and the overall evolution of the solid Earth. Mid-ocean ridge basalts, the volcanic rocks that make up the oceanic crust, are generated by partial melting of dry or nearly dry mantle rock as it rises and decompresses beneath the spreading center. And the amount of melting and the thickness of the crust produced depend on mantle temperature and on the presence of any water in the source region. If the mantle was wetter in the past, as might be expected if Earth was hotter and convecting more vigorously and subducting water faster, then mid-ocean ridge volcanism might have produced thicker crust and larger volumes of magma. Though the relationship is complex because higher temperatures also promote more melting, independently of water content. The generation of continental crust is more directly linked to water because the magmas that build continents are produced primarily at subduction zones where water released from the descending slab triggers melting in the mantle wedge. And these water-rich magmas have chemical compositions that differ from dry melts, being enriched in silica and in elements that are transported by water during fluid rock interactions. If the efficiency of water recycling at subduction zones has changed over time, then the rate of continental crust generation may also have changed, potentially explaining observations that suggest continental crust was produced more rapidly in certain periods of Earth's history than in others. The presence of water in mantle melts also affects the behavior of magma as it rises through the crust. Because water dissolved in magma lowers its viscosity and lowers the temperature at which it crystallizes, allowing water-rich magmas to remain liquid and mobile at shallower depths and lower temperatures than dry magmas. When water-rich magma approaches the surface and pressure decreases, the dissolved water can exhaled from the liquid to form gas bubbles. And if this happens rapidly, the expansion of gas can fragment the magma and drive explosive volcanic eruptions, creating the violent pyroclastic eruptions characteristic of subduction zone volcanoes. Continental roots and hidden water. Beneath the continents, particularly beneath the oldest and most stable continental regions called cratons, the lithosphere extends to depths of over 100 miles, much deeper than the oceanic lithosphere, which is typically only about 60 miles thick. And this thick continental lithosphere may contain significant amounts of water stored in minerals, even though it is generally cooler and less hydrated than oceanic lithosphere, because it has not been recently in contact with seawater. The deep continental lithosphere consists of mantle rock that has been chemically modified through ancient episodes of melting, and that has remained attached to the overlying continental crust for billions of years, resisting recycling into the mantle through subduction because continental crust is too buoyant to be subducted. This ancient lithospheric mantle is cold and strong compared to the underlying asthenosphere, creating a barrier that resists deformation and that helps preserve the continents against destruction by tectonic forces. Studies of xenoliths, fragments of deep lithosphere brought to the surface by volcanic eruptions, show that continental lithospheric mantle contains a variety of hydrous minerals, including phlogopite and amphibolite, that can hold 1 or 2% water by weight. And though these minerals make up only a small fraction of the total rock volume, their presence means that the continental lithosphere as a whole may contain a significant water reservoir. The amount of water in continental lithosphere is uncertain and varies from region to region, depending on the geological history and the processes that formed and modified each cratonic root. But estimates suggest that the total could be comparable to an ocean's worth of water distributed through the hundreds of miles of thick lithosphere beneath all the world's continents. This water is ancient, potentially dating back billions of years to the time when the continental lithosphere formed, and it is largely isolated from the active water cycle because it is not being subducted and it is not being melted and erupted through volcanism under most circumstances. However, if the continental lithosphere is somehow disturbed, perhaps by collision with another continent or by the intrusion of a mantle plume, the heating and deformation can release water from the lithospheric minerals, potentially triggering melting and creating unusual volcanic activity in continental interiors far from plate boundaries. Serpentinite and hydration. Among the most important water-bearing rocks in the deep earth are serpentinites, rocks that form when mantle peridotite reacts with water at relatively low temperatures, transforming olivine and pyroxene minerals into serpentine minerals that contain around 13% water by weight, making them among the most hydrous rocks in Earth's interior. Serpentinization occurs primarily at mid-ocean ridges, where seawater circulates through fractures in the oceanic lithosphere and reacts with mantle rock exposed at the seafloor, and in the outer parts of subduction zones where water released from the descending slab reacts with the overlying mantle wedge. The process of serpentinization involves complex chemical reactions where magnesium and iron from olivine and pyroxene combine with water and dissolved silica to form serpentine minerals, releasing heat and producing hydrogen gas as a byproduct through reactions between iron in the rock and water. This hydrogen production makes serpentinite systems potential habitats for chemosynthetic life that can use the hydrogen as an energy source. And some scientists speculate that life may have originated in serpentinite-hosted hydrothermal systems, either on early Earth or possibly on other planets and moons, where similar conditions might exist. Serpentinization dramatically changes the physical properties of rock, reducing its density and its strength and making it much more susceptible to deformation. And large volumes of serpentinized mantle in subduction zones or at mid-ocean ridges can influence tectonic processes by creating weak zones where faulting and deformation are concentrated. When serpentinite is carried into the mantle through subduction, it remains stable up to depths of about 60 miles and temperatures of about 1200 degrees Fahrenheit. Conditions typically found near the top of the descending slab, but at greater depths and higher temperatures, the serpentine minerals break down, releasing their water, which then percolates upward into the mantle wedge, or is incorporated into deeper hydrous minerals that are stable at higher pressure and temperature. The transformation of serpentinite to dry mantle minerals releases large volumes of water in a relatively narrow depth range, creating a concentrated zone of fluid release that is thought to be particularly important for triggering melting in the mantle wedge and for generating the arc volcanoes that characterize subduction zones. The slow movement downward. As tectonic plates descend into the mantle at subduction zones, they move slowly but steadily downward at rates typically between 2 and 10 centimeters per year, speeds that seem negligibly slow, but that over millions of years transport vast volumes of material from the surface into the deep earth, and that accomplish the work of recycling oceanic lithosphere through the entire mantle. The angle of subduction varies considerably from one subduction zone to another, with some slabs descending steeply at angles approaching vertical, while others descend at shallow angles of 20 or 30 degrees. And this variation in geometry affects how deep the slab reaches before heating up and releasing its water. Steep slabs penetrate quickly to greater depths and remain colder for longer, allowing them to carry water deeper into the mantle, while shallow slabs spend more time at relatively shallow depths where they heat up faster and release water at shallower levels. The fate of the subducting slab as it descends into the mantle has been debated for decades, with early plate tectonics theory assuming that slabs would heat up and be assimilated into the surrounding mantle at depths of a few hundred miles, while more recent seismic imaging has shown that many slabs penetrate through the entire mantle and accumulate in a layer above the core mantle boundary where they may remain for hundreds of millions of years. The ability of slabs to penetrate into the lower mantle depends partly on their temperature and density and partly on the viscosity structure of the transition zone and uppermost lower mantle. An observation suggests that some slabs stagnate temporarily in the transition zone before eventually continuing their descent, while others appear to descend more continuously. The water content of the slab influences its trajectory because hydrated minerals are less dense than their dry equivalents, making the slab slightly more buoyant and possibly affecting whether it sinks smoothly or encounters resistance at the base of the transition zone, where density contrasts between the slab and surrounding mantle may be small. Understanding slab dynamics is important for understanding the deep water cycle, because it determines how much water can be transported past the transition zone into the lower mantle versus how much is retained in the transition zone or released to shallower depths. Lower mantle and water storage. Below the transition zone, in the lower mantle extending from about 410 miles to 1,800 miles depth, the dominant minerals are bridgemanite and ferropericlase, which together make up about 90% of the Earth's volume and which have much lower water storage capacity than the transition zone minerals wadsleyite and ringwoodite. Laboratory experiments on bridgemanite show that it can incorporate at most a few hundredths of a percent water by weight, roughly 10 to 50 times less than ringwoodite, and ferropericlase appears to hold even less water. This dramatic reduction in water storage capacity at the transition zone lower mantle boundary means that water cannot easily pass from the transition zone into the lower mantle in dissolved form in minerals, and if a water-rich transition zone exists, there should be a sharp contrast in water content across this boundary. However, water entering the lower mantle might not necessarily be stored in bridgemanite and ferropericlase, but could instead form separate hydrous phases. Minerals composed primarily of water with minor amounts of magnesium and silicon that could exist as distinct layers or pockets in the lower mantle. Several such high-pressure hydrous phases have been discovered in laboratory experiments, including phase D and phase H, both of which are stable at lower mantle pressures, and which can contain around 10 to 15% water by weight. And if such phases are present in the lower mantle, they could provide significant water storage, even though the dominant silicate minerals are nearly dry. The existence and abundance of these hydrous phases in the actual lower mantle is uncertain and controversial, with some scientists arguing that they should be common wherever cold subducted slabs carry water into the lower mantle, and others arguing that the conditions necessary for their formation are rare, and that most lower mantle is very dry. Seismic observations provide ambiguous evidence, with some studies suggesting the presence of thin layers of anomalous material at the base of the transition zone that could be hydrous phases, while other studies find no clear evidence for such layers. The question of lower mantle water storage is important for understanding the long-term evolution of Earth's water, because if significant amounts of water are sequestered in the lower mantle, this represents a long-term sink that could gradually dry out the surface oceans over billions of years. The core mantle boundary region. At the base of the mantle, about 1,800 miles beneath our feet, the solid silicate rock of the mantle meets the liquid iron alloy of the outer core at a boundary that is the most dramatic internal interface in the planet, marking enormous contrasts in composition, temperature, and density. This core mantle boundary region is fascinating to geophysicists because it influences Earth's magnetic field, affects heat flow from the core that drives mantle convection, and appears to have complex structure, including zones of partial melt and unusual materials that have accumulated there over Earth's history. Seismic studies reveal that some regions of the core mantle boundary have reduced seismic velocities and unusual properties, suggesting the presence of partially molten material or chemically distinct rock. And these regions correlate with areas where mantle plumes are thought to originate, suggesting a connection between core mantle boundary processes and surface volcanism. Water could potentially reach the core mantle boundary through subduction if cold slabs penetrate the entire mantle, carrying hydrous minerals or hydrous phases. And some scientists speculate that chemical reactions between water or hydrous minerals and the iron-rich core could occur at the boundary, extracting oxygen from water and hydrogenating the core while oxidizing iron at the base of the mantle. Such reactions would have important consequences for core dynamics and for the generation of Earth's magnetic field. And they could provide a sink for water that makes it very difficult for water to return to the surface, essentially locking it away permanently in the deep Earth. Evidence for water at the core mantle boundary is indirect and speculative, based mainly on theoretical calculations and laboratory experiments showing that such reactions are possible under the extreme pressure and temperature conditions there. But direct observational confirmation is lacking, and the question remains open. The potential existence of water at the core mantle boundary illustrates how the deep water cycle might extend through the entire planet, connecting surface oceans to the metallic core through a chain of processes operating across 1,800 miles of rock and over billions of years of time. Volcanic outgassing through ages. Throughout Earth's history, volcanic eruptions have been the primary mechanism returning water from the mantle to the surface, releasing steam and other volcanic gases into the atmosphere, where they condense to form rain and eventually accumulate as oceans and ice. The rate of volcanic outgassing has varied over geological time, depending on the vigor of mantle convection, the rate of plate tectonics, the amount of water in the mantle available to be released, and the distribution of that water among different depths and reservoirs. In Earth's early history, when the planet was hotter and had more radiogenic heat production from short-lived radioactive isotopes that have since decayed, mantle convection was more vigorous, and the rate of volcanism was probably higher than today, potentially leading to more rapid outgassing of mantle volatiles, including water, carbon dioxide, and nitrogen. Some models suggest that early Earth's atmosphere was much denser and richer in water vapor and carbon dioxide than the present atmosphere, creating a strong greenhouse effect that kept the surface warm despite the sun being about 30% less luminous than today. And that over billions of years, as the planet cooled and as water accumulated at the surface forming oceans, the atmosphere gradually evolved toward its current composition. The early oceans may have been smaller than today, because much of Earth's water was still dissolved in the hot mantle. And as the mantle cooled and convection slowed, water was gradually extracted through volcanism and accumulated at the surface, growing the oceans over time. Alternatively, if Earth accreted most of its water late in the formation process through impacts of water-rich asteroids and comets, the oceans might have formed relatively quickly once the bombardment ended and surface temperatures dropped below the boiling point of water. And subsequent outgassing from the mantle would have supplemented rather than created the surface water reservoir. The history of volcanic outgassing is recorded imperfectly in the geological record through studies of ancient volcanic rocks and their volatile contents, through measurements of isotopic ratios that trace the sources of volcanic gases, and through models of atmospheric evolution constrained by observations of how atmospheric composition has changed over time, based on geochemical proxies preserved in sedimentary rocks. Hydrous minerals in mid-ocean ridge. Beneath the mid-ocean ridges where tectonic plates pull apart and new oceanic crust forms. The upwelling mantle undergoes decompression melting and generates basaltic magma that rises to create the volcanic rocks of the seafloor. And this process operates today, much as it has for hundreds of millions of years, continuously producing roughly 8 square miles of new oceanic crust annually. The mantle beneath mid-ocean ridges is relatively dry compared to subduction zones, containing typically just a few hundredths of a percent water by weight. But even this small amount of water influences the melting process and the composition of the resulting basalts. As mantle rock rises beneath the ridge, pressure decreases, and when the rock crosses its solidus, the temperature at which it begins to melt, a small fraction of the rock melts and the liquid magma separates from the solid residue. Water strongly partitions into the liquid phase during melting, meaning that even if the source mantle contains only a trace of water, the magma produced by melting will be enriched in water, typically containing a few tenths of a percent water by weight. This water is ultimately derived from the mantle and represents water that has been cycling through the deep earth for potentially hundreds of millions or billions of years since it was last at the surface. When the basaltic magma reaches the seafloor and erupts as lava, most of its dissolved water is released into the ocean as volcanic gas. But some water remains dissolved in the rapidly cooled volcanic glass that forms when lava meets seawater. After the crust forms, seawater circulates through it in hydrothermal systems, reacting with the rock and creating hydrous minerals, effectively rehydrating the crust and preparing it for eventual subduction that will carry this water back into the mantle, closing the loop of the deep water cycle. The mid-ocean ridges thus serve as sites where water exits the mantle through volcanism and re-enters through hydrothermal alteration, maintaining a balance that has apparently kept the oceans at roughly constant volume for at least hundreds of millions of years, and possibly for much longer. Diamonds as messengers from depth. Let us drift more deeply now into contemplation of how diamonds form and what they tell us about water in Earth's deep interior, allowing these thoughts to slow and soften like crystals growing in the patient darkness far below. Diamonds crystallize from carbon in the mantle under conditions of high pressure and temperature, typically at depths greater than about 90 miles, where pressure exceeds 40,000 times atmospheric pressure. And the carbon source can be either organic carbon subducted from the surface, carbon dioxide dissolved in mantle fluids or melts, or primordial carbon that has been in the mantle since Earth's formation. Most gem-quality diamonds come from ancient continental lithosphere, where they formed billions of years ago and remained stored in the cold, stable roots beneath cratons until volcanic eruptions called kimberlites brought them rapidly to the surface, carrying diamonds upward at speeds fast enough to prevent them from converting to graphite or burning in the oxygen-rich atmosphere during ascent. The kimberlite eruptions are rare and violent events driven by carbon dioxide gas that flashes into bubbles as the magma approaches the surface, creating explosive volcanism that carves pipe-shaped conduits through the crust and spreads diamond-bearing debris across the surface. Diamond exploration companies search for these kimberlite pipes because they are the only commercially viable sources of natural diamonds. And the pipes that contain the most diamonds and the largest gems are those that sample the deepest and oldest parts of the continental lithosphere, where conditions for diamond formation have been stable for billions of years. The mineral inclusions trapped inside diamonds provide our only direct samples of deep mantle rock, because all other mantle samples available to us come from shallower depths or have been modified during their journey to the surface. By analyzing these inclusions using techniques including electron microscopy, X-ray diffraction, and infrared spectroscopy, scientists can determine what minerals exist at depth, what their chemical compositions are, and whether they contain water. The discovery of water-bearing ringwoodite in a diamond provided direct proof that the transition zone can hold significant water, confirming decades of laboratory experiments and theoretical predictions, and subsequent discoveries of other hydrous minerals in diamonds continue to expand our knowledge of deep earth water. The patient crystallization, diamonds grow slowly in the mantle, adding carbon atoms one at a time to their crystal structures over periods that may span millions of years. And during this growth, they occasionally trap small grains of surrounding minerals as inclusions, freezing these minerals in place and preserving them as they were at the time of trapping. The growth rate of diamonds is not well constrained, but is estimated to be extraordinarily slow, perhaps a few micrometers per million years, meaning that even a small diamond, a few millimeters across, would take tens of millions of years to grow. This slow growth occurs in environments where carbon-bearing fluids, or melts, saturated with carbon, percolate through mantle rock, depositing carbon as diamond in fractures or in pores where conditions are suitable. The formation of diamonds requires not just high pressure, but also specific chemical conditions, including relatively oxidizing conditions that favor diamond over graphite, and the presence of fluids or melts that can transport carbon and allow crystals to grow. Water plays a role in diamond formation because water-rich fluids in the mantle can dissolve carbon and transport it to sites where diamonds nucleate and grow. And the chemical interactions between water and mantle minerals help create the oxidizing conditions that stabilize diamond. Some diamonds contain fluid inclusions, tiny bubbles of liquid, or was trapped during growth. And analysis of these fluids shows that they are often water-rich brines containing dissolved salts and other compounds, demonstrating that water is present and mobile in the diamond-forming environment. The isotopic composition of carbon in diamonds provides information about carbon sources, with some diamonds showing isotopic signatures characteristic of organic carbon from the surface that was subducted and transported to depth, while other diamonds have isotopic compositions consistent with primordial mantle carbon. The mixture of carbon sources and the presence of water-rich fluids suggest that the carbon cycle and the water cycle in the mantle are intimately connected, with both elements being transported by subduction, stored in various reservoirs, and eventually returned to the surface through volcanism. Earthquakes and water's role. Earthquakes occur when rocks suddenly break and slip along faults, releasing elastic strain energy that has accumulated over years to centuries as tectonic forces slowly deform the crust and upper mantle. And the presence of water influences where earthquakes occur, how deep they can occur, and how large they can become. In the shallow crust, water in fractures and pores increases pore pressure, which reduces the effective stress holding rocks together, making it easier for faults to slip and potentially triggering earthquakes in regions where stress is already close to failure. This effect is well documented in cases of induced seismicity, where human activities such as fluid injection into deep wells for wastewater disposal or hydraulic fracturing increase pore pressure and trigger earthquakes, sometimes in regions with no previous history of seismic activity. In subduction zones, earthquakes occur at much greater depths than in most other tectonic settings, with the deepest earthquakes occurring at depths of about 430 miles in the transition zone beneath some subduction systems. These deep earthquakes cannot be explained by the same brittle fracture mechanism that produces shallow earthquakes, because at the high temperatures and pressures of the deep mantle, rocks should deform plastically rather than breaking. And yet, seismic waves clearly show sudden ruptures occurring at these depths. The explanation for deep earthquakes remains somewhat uncertain, but involves water released from hydrous minerals in the subducting slab. As the slab descends and heats up, it passes through a series of metamorphic reactions where hydrous minerals break down and release water. And these dehydration reactions occur at specific temperatures and pressures corresponding to specific depths in the slab. When a large volume of hydrous minerals suddenly dehydrates and releases water, the reaction can proceed unstably, accelerating once it starts and releasing stress through a rapid transformation from hydrous to dry mineral assemblages. This transformation can nucleate fractures even in otherwise ductile rock and can trigger runaway failure that produces an earthquake. The depth distribution of earthquakes in subduction zones correlates with the expected depths of dehydration reactions, supporting the connection between water release and deep seismicity. And detailed studies of earthquake locations and mechanisms provide insights into which minerals are dehydrating and how water is distributed in the slab. Geochemical tracers and isotopes. The movement of water through Earth's interior leaves chemical signatures that can be detected and studied through analysis of volcanic rocks and gases, providing indirect information about deep water cycling, even though we cannot directly sample most of the mantle. Different sources of water in the Earth system have different isotopic compositions, ratios of heavy to light isotopes of hydrogen and oxygen. And these isotopic signatures are preserved during many geological processes, allowing scientists to trace where water came from and how it has been modified. Water at Earth's surface has a hydrogen isotopic composition dominated by the light isotope hydrogen-1, but also containing trace amounts of deuterium or hydrogen-2. And the ratio of deuterium to hydrogen is expressed as delta D, a measure that compares the sample to a standard. Water that is equilibrated with mantle minerals tends to have slightly different delta D values than surface water, because the isotopes fractionate differently at high temperature, with the heavier isotope preferentially incorporating into certain mineral sites, while the lighter isotope remains in fluids. By measuring the delta D of water extracted from volcanic glasses or from hydrous minerals in mantle rocks, scientists can determine whether that water came recently from the surface, has been cycled through the mantle, or represents primordial water that has been in the mantle since Earth's formation. The results generally show that water in mid-ocean ridge basalts and in mantle xenoliths has isotopic compositions consistent with deep mantle sources, supporting the existence of water that has resided in the mantle for long periods. While water in arc volcanoes above subduction zones shows isotopic evidence of mixing between mantle water and water recently subducted from the surface. Oxygen isotopes provide complementary information because oxygen from seawater that has reacted with rock at low temperature has a distinctive isotopic signature compared to magmatic oxygen. And this signature can be used to trace recycled surface materials in the mantle. Noble gas isotopes, including helium-3 and argon-40, also provide tracers of mantle sources and mixing, because the mantle contains primordial noble gases trapped during Earth's formation that have different isotopic ratios than atmospheric gases. And volcanic rocks that tap deep mantle sources show different noble gas signatures than those that tap shallow recycled materials. Computer models and simulations. Understanding how water moves through Earth's interior and how it affects mantle processes requires combining observations with computer models that simulate mantle convection, plate tectonics, and water cycling over millions of years, because the processes operate too slowly and at depths too great to observe directly in action. These numerical models use mathematical equations that describe how rocks deform and flow under stress, how heat is transported by conduction and convection, how chemical species diffuse and react, and how water partitions between minerals and melts. And they solve these equations using powerful computers that can handle the complex three-dimensional geometry and the enormous range of timescales involved. The models begin with initial conditions representing Earth at some time in the past, specify boundary conditions such as the temperature at the core mantle boundary and the heat flux at the surface, and then let the system evolve forward in time according to the physical laws encoded in the equations, tracking how temperature, pressure, composition, and water content change throughout the mantle over millions of simulated years. Results from these models can be compared to observations, including the present-day distribution of earthquake locations that trace subducting slabs and upwelling plumes, the distribution of seismic velocities that reflect temperature and composition, the chemistry and isotopic composition of volcanic rocks, and the rates of plate motions and sea level change that reflect the balance between water subduction and outgassing. The models help test hypotheses about deep water cycling by allowing scientists to explore what would happen under different assumptions about water storage capacity in different mantle regions, about the efficiency of water subduction, about the residence time of water in the transition zone, and about the rate of water return to the surface through volcanism and metamorphism. Early models of mantle convection treated water implicitly or ignored it entirely, but increasingly sophisticated models now explicitly track water as it moves through the system, calculating how water affects melting and viscosity, and how these effects feed back to influence convection patterns and plate tectonics. The models suggest that Earth's deep water cycle has probably been operating for billions of years, and that it plays an important role in regulating mantle temperature, controlling the style of plate tectonics, and maintaining oceans at the surface. Mars and the missing ocean. As we continue our gentle descent into understanding planetary water cycles, it is illuminating to consider how Earth compares to other rocky planets in our solar system, particularly Mars, which shows strong evidence of having had substantial surface water in its distant past, but which today is a frozen desert with only traces of water ice at its poles and no liquid water on its surface. Mars is about half Earth's diameter and has only about 1/10 Earth's mass, and this smaller size had profound consequences for its thermal evolution, because smaller planets have less internal heat and cool more quickly, and because they have smaller gravitational pull that makes it harder to retain atmospheric gases against escape to space. Early Mars likely had a thicker atmosphere that created warmer surface conditions, allowing liquid water to exist. And geological features including ancient river valleys, lake beds, and possible shorelines suggest that Mars once had oceans or large lakes covering parts of its surface. However, Mars lacks plate tectonics and does not appear to have ever had Earth-style subduction that could cycle water between surface and interior, and without plate tectonics to recycle gases from the surface into the interior and back. Mars gradually lost its atmosphere as gases escaped to space and as water reacted with surface rocks to form hydrated minerals. Today, Mars's water is locked in polar ice caps, in permafrost beneath the surface, and chemically bound in minerals, with no active water cycle comparable to Earth's. The contrast between Earth and Mars illustrates how planetary size and the presence of plate tectonics are crucial for maintaining surface water over billions of years, and it suggests that Earth's deep water cycle operating through subduction and volcanic outgassing has been essential for keeping our planet habitable by regulating atmospheric composition and maintaining oceans. Some scientists speculate that Mars's interior may contain water sequestered in minerals similar to Earth's mantle, though we have no direct evidence for this, and Mars's different thermal history and lack of plate tectonics would have created very different conditions for water storage and cycling. Future missions to Mars, including sample return missions that would bring Martian rocks to Earth for detailed analysis, may provide insights into how much water Mars retains in its interior, and how that water has been cycled and stored over the planet's history. Water and planetary habitability. The presence of liquid water at Earth's surface is generally considered essential for life as we know it. And understanding how Earth has maintained surface water for billions of years, despite the many processes that could have dried out the planet, helps us understand the requirements for planetary habitability and informs the search for life on other worlds. A planet needs to be the right distance from its star so that temperatures allow liquid water, rather than having all water frozen or boiled away, and Earth sits comfortably in the sun's habitable zone where conditions are suitable. However, distance from the star is not the only factor determining whether a planet can maintain liquid water, because atmospheric greenhouse gases can warm a planet that would otherwise be too cold. And a thick atmosphere can maintain surface pressure sufficient to allow liquid water at higher temperatures than would be possible with low pressure. Earth's early history, when the sun was fainter, would have resulted in a frozen surface unless greenhouse gases, including water vapor and carbon dioxide, kept the planet warm. And the ability to maintain these gases in the atmosphere depends on the balance between volcanic outgassing that adds gases and various removal processes, including chemical weathering and escape to space. Plate tectonics plays a crucial role in this balance through the carbonate-silicate cycle, a feedback system where atmospheric carbon dioxide dissolves in rainwater to form carbonic acid that weathers silicate rocks, and the resulting dissolved ions wash into the ocean where they precipitate as carbonate minerals, locking carbon away in sediments that are eventually subducted and heated, releasing carbon dioxide back into the atmosphere through volcanic activity. This cycle regulates atmospheric carbon dioxide over millions of years, preventing it from accumulating to levels that would overheat the planet or from dropping to levels that would freeze the surface. And it operates because of the deep carbon and water cycles enabled by plate tectonics. Planets without plate tectonics cannot operate this cycle and may be more vulnerable to losing their atmospheres and water over time, as Mars apparently did. The deep water cycle also helps maintain surface habitability by preventing all of Earth's water from being subducted into the mantle, because volcanic outgassing returns water to the surface at a rate that apparently balances subduction, keeping the ocean volume roughly constant. If this balance were disrupted and subduction removed water faster than volcanism returned it, the oceans would gradually shrink and eventually disappear, making the surface uninhabitable for life that depends on water. Future evolution of Earth's water. Looking forward into the distant future, we can use our understanding of the deep water cycle to predict how Earth's water distribution might change over billions of years as the planet continues to cool and evolve. Though such predictions are uncertain because they depend on assumptions about processes we do not fully understand. As Earth's interior gradually cools due to heat loss to space, mantle convection will slow and the rate of plate tectonics will decline, potentially reducing both the rate at which water is subducted into the mantle and the rate at which water is returned to the surface through volcanism. If these rates decline proportionally, the ocean volume might remain approximately constant even as the overall rate of water cycling decreases. But if they decline at different rates, the balance could shift toward net loss or net gain of surface water. Some models suggest that as subduction slows, the return of water through volcanism will slow even more, leading to net loss of surface water as it continues to be pulled into the mantle by ongoing subduction, while volcanic outgassing becomes less effective at replacing it. Over timescales of billions of years, this could lead to significant reduction in ocean volume or even complete loss of surface oceans, drying out the planet and making it uninhabitable for life. However, these predictions are highly uncertain because we do not know how much water is currently in the mantle, how water storage capacity changes as the mantle cools and minerals adjust to lower temperatures, and whether water that enters the lower mantle can eventually return to the surface or becomes permanently sequestered. An alternative possibility is that as the mantle cools, minerals in the transition zone and upper mantle become able to hold more water than they can at higher temperatures, causing the mantle to gradually absorb water from the surface and store it in solid mineral structures, shrinking the oceans over time. Another factor affecting Earth's future water budget is the gradually increasing luminosity of the sun, which is about 30% brighter now than when Earth formed and will continue to brighten as it ages, eventually reaching a point about 1 billion years from now, when the increased solar heating will cause Earth's oceans to evaporate into the atmosphere, creating a runaway greenhouse effect that will make the surface too hot for liquid water regardless of how much water remains in the mantle. This distant future represents the end of Earth's habitability for life as we know it. And it will precede the sun's eventual evolution into a red giant that will engulf the inner planets about 5 billion years from now. Methods of detection deep below. Scientists studying the deep Earth use a variety of techniques to detect water and map its distribution, compensating for the impossibility of directly accessing most of the mantle by developing indirect methods that infer water content from observable properties. Seismic imaging is perhaps the most powerful tool, using earthquake waves that propagate through the entire planet to probe internal structure. Because the speed of seismic waves depends on the temperature, pressure, composition, and water content of the rocks they travel through. And by measuring how wave speeds vary in different regions, scientists can infer variations in these properties. Water generally slows seismic waves compared to dry rock because it reduces the elastic moduli of minerals, making them slightly softer and more compressible. And so regions of anomalously slow seismic velocities in the deep mantle could indicate the presence of water, though other factors like high temperature or partial melting also slow seismic waves and must be considered. Seismic imaging has revealed large, low-velocity provinces in the deep mantle beneath Africa and the Pacific. And while these are generally interpreted as hot, upwelling mantle plumes, some scientists have suggested that they might also contain water. Electrical conductivity measurements provide another window into deep water, because water and hydrous minerals conduct electricity much better than dry minerals. And electromagnetic induction experiments that measure how Earth's magnetic field induces electrical currents in the mantle can constrain conductivity structure at depth. High conductivity in the transition zone detected in several regions has been interpreted as evidence for water-bearing minerals, though again, other explanations including metallic iron or graphite could also produce high conductivity. Laboratory experiments on minerals synthesized at high pressure and temperature in diamond anvil cells and large volume presses provide essential data on water storage capacity, on how water affects physical properties, and on the stability of hydrous minerals under mantle conditions. These experiments are challenging because they must recreate the extreme conditions of the deep Earth, maintaining pressures exceeding 1 million times atmospheric pressure and temperatures exceeding 2,000 degrees Fahrenheit, while making precise measurements on tiny samples. But advances in experimental techniques continue to improve our ability to study deep Earth materials. Analysis of natural samples, including mantle xenoliths brought up in volcanic eruptions, ophiolites, which are slices of oceanic lithosphere thrust onto continents during collisions, and mineral inclusions in diamonds, provides ground truth about actual mantle composition and water content in specific locations. The stillness of deep time. As we drift even deeper into our exploration, moving more slowly now through concepts that invite contemplation rather than analysis, let us appreciate the profound stillness and patience of the deep Earth's water cycle, operating on timescales so vast that the entire span of human civilization appears as less than a single breath, less than the blink of an eye in the long, slow rhythm of geological processes. Water molecules locked in minerals hundreds of miles below the surface may remain there for hundreds of millions of years, held in crystal structures that change so slowly that the notion of motion almost loses meaning, waiting patiently through eras when entire species evolved and went extinct. When continents drifted across the globe and collided to form supercontinents before breaking apart again. When mountains rose and eroded away to nothing, all while that water molecule sat motionless in its mineral cage deep in the darkness. The deep Earth does not hurry, does not respond to urgency or anxiety, does not care about human timescales or human concerns, but simply exists in its own eternal present, following the inevitable consequences of heat and pressure and chemistry, with a patience that makes waiting an active verb rather than a passive state, that makes stillness a kind of motion stretched across so much time that it becomes imperceptible. The transition zone holds water the way the ocean holds water, as a vast reservoir that accepts and releases over immense timescales, maintaining balance not through active regulation, but through the passive operation of physical laws, through the automatic responses of minerals to changing conditions, through the slow, steady march of thermodynamics toward equilibrium. There is something deeply calming about contemplating these timescales, about recognizing that beneath our feet, the planet operates in geological time where our entire lives are insignificant, yet where the processes that shaped our existence and that make our lives possible continue their patient work. Indifferent to human awareness, but nonetheless sustaining the conditions that allow consciousness to briefly arise and contemplate its own foundations. The unity of Earth's water, all of Earth's water, whether visible in oceans or frozen in glaciers or vapor in the atmosphere, or locked in minerals deep in the mantle, is connected through the great cycles that move water between reservoirs over timescales ranging from days for the surface hydrological cycle to hundreds of millions of years for the deep geological cycle. And understanding this unity helps us appreciate that we are not separate from these processes, but participate in them. Breathing water that evaporated from the ocean, drinking water that fell as rain, living in bodies built from water that has cycled through the Earth system countless times. The water in your cells has been part of dinosaurs and ancient seas, has been frozen in glaciers and buried in sediments, has circulated through hydrothermal systems at mid-ocean ridges, and has been subducted into the mantle, where it resided in minerals for millions of years before being erupted in a volcano and rained back onto the surface, where eventually it found its way into your body for this brief moment before continuing its endless journey through the water cycle. This perspective of unity and connection extends beyond individual organisms to encompass the entire planet, revealing Earth not as a collection of separate compartments, but as an integrated system where everything is connected to everything else through the flow of matter and energy, where the oceans and the mantle are not separate, but are in communication through subduction and volcanism, where the atmosphere and the solid Earth exchange gases and participate together in regulating climate and maintaining habitable conditions. The hidden water in Earth's deep interior is not separate from the visible water at the surface, but is the same water in a different phase of its journey, temporarily stored in mineral structures, but eventually to be released and returned upward. While surface water continuously cycles downward, replacing what was released, maintaining a dynamic balance that has operated throughout Earth's history, and that will continue into the future as long as Earth remains geologically active. Drifting toward deep rest. Now, as our journey through Earth's hidden waters approaches its gentle conclusion, let us allow our thoughts to settle like sediments, drifting slowly downward through still water. Coming to rest on the quiet floor of understanding, no longer actively seeking, but simply being present with what we have discovered together. The deep earth holds its water patiently in darkness and silence, in minerals that change slowly and in processes that operate without hurry. And we can learn from this patience and this stillness, allowing ourselves to rest in the knowledge that beneath all the surface motion and change, there exists a deeper stability, a foundation that has endured for billions of years and that will endure for billions more. The water molecules in the transition zone, hundreds of miles below us, are not aware of their situation, do not know they are water, do not anticipate their eventual release and return to the surface, but simply exist in the eternal now of their crystal structure, participating in the vast, slow circulation of matter through the planet without intention or awareness. We who possess awareness can appreciate this on their behalf, can marvel at the beauty and complexity of the system they inhabit, can find peace in contemplating processes so much larger and longer lasting than ourselves. As you rest now and prepare to drift into sleep, imagine yourself descending slowly through layers of rock, feeling the pressure increase gently, feeling the temperature rise gradually, descending past the crust and into the mantle, past the upper mantle into the transition zone where water is stored in minerals, settling into that deep, quiet place where change happens so slowly it is almost stillness, where time stretches out so far that past and future lose their distinction and there is only the endless, peaceful present. Let the weight of the rock above you be not a burden, but a comfort, a warm, heavy blanket that holds you safely in place, preventing motion, encouraging rest, supporting complete relaxation. Let the darkness be not frightening, but peaceful, a soft velvet darkness that asks nothing and gives the gift of rest. Let yourself become like water in a mineral, held gently in a crystal structure, locked in place but not trapped, simply existing in patient stillness while geological processes happen around you at their own unhurried pace. The eternal cycle continues. And so we complete our journey into Earth's hidden water reservoirs, having descended from the familiar surface through the crust and upper mantle into the transition zone where water is stored in quantities rivaling the surface oceans, and having learned about the processes that move water between these reservoirs over hundreds of millions of years through the coupled action of subduction, mineral transformation, melting, and volcanism. We have discovered that Earth is not a dry, rocky planet with a thin skin of surface water, but is instead thoroughly hydrated throughout much of its interior, with water playing essential roles in plate tectonics, in volcanic activity, in mantle convection, and in maintaining the surface habitability that makes life possible. We have learned that this water cycles slowly through the planet, subducting from surface to depth, residing in the interior for immense periods, and eventually returning to the surface through volcanic outgassing and metamorphic processes, maintaining a balance that has kept oceans at Earth's surface for billions of years. We have seen that studying this hidden water requires indirect methods because we cannot access the deep mantle directly, and that scientists use combinations of seismic imaging, laboratory experiments, computer modeling, and analysis of rare natural samples to constrain how much water exists at depth and how it is distributed and stored. we have contemplated the profound timescales on which the deep water cycle operates. Timescales so vast that they challenge human comprehension, but that are the natural pace of planetary evolution. And we have reflected on how Earth compares to other planets and how the presence of plate tectonics and deep water cycling may be essential requirements for long-term planetary habitability. As you rest now in the deep peace that comes from understanding your connection to these planetary processes, knowing that you are made of water that has cycled through Earth's interior over billions of years and that will continue cycling long after you are gone. Let yourself feel held by the planet's gravity, supported by the solid ground, connected through invisible threads to the deep reservoirs of water that make your existence possible. The water in the transition zone continues its patient existence, locked in minerals that wait without knowing they are waiting, participating in the great cycle that will eventually bring them back toward the surface, though that return may take hundreds of millions of years. And in that patience and that stillness, there is a lesson about rest and about letting go of urgency, about allowing natural processes to unfold at their own pace without trying to hurry them. Sleep now with the knowledge that deep beneath you, water is stored safely in the Earth's interior, that this water has been there for eons and will be there for eons more, that the planet's water cycle continues its eternal circulation, regardless of human awareness or concern, operating according to physical laws that cannot be changed or circumvented, following the path of least resistance through phase transformations and chemical reactions that happen automatically when conditions are right. Let this knowledge of deep time and deep water ease you into deep sleep, resting in the embrace of geological processes that dwarf individual human lifetimes, but that collectively created the conditions for human existence, and that continue to maintain those conditions through their patient operation. The hidden oceans beneath us remind us that much of what is real and important is invisible and inaccessible to direct observation, known only through careful inference and indirect detection, yet no less real for being hidden, and perhaps even more worthy of wonder for requiring imagination and intellect to appreciate. Rest now in the darkness and silence of the deep earth, in the quiet spaces between crystals where water molecules wait, in the slow, steady circulation that moves matter through the planet over hundreds of millions of years, in the timeless patient rhythm of geological processes that know nothing of haste or hurry but simply unfold according to the laws of physics and chemistry, inexorably and eternally, as you drift gently into sleep. The descent through the crust, entering the planet's hidden pathways. The crust is far more than a rigid platform beneath our feet. It is a living archive of Earth's long evolution, an intricate mosaic of minerals formed under different conditions and at different times. Some layers were once molten rock that cooled slowly deep underground. Others were sediments deposited by ancient oceans, compressed into stone over millions of years. Still others are fragments of continents that collided and fused, stitched together through tectonic forces. As we drift downward, we encounter these layers like chapters in a story, each one preserving a moment in Earth's history, each one shaped by processes that operated on timescales far beyond human experience. Water, in the crust, behaves in ways we understand. It flows, seeps, infiltrates, and collects. It moves through porous rocks, through fractures left by ancient earthquakes, through networks of tiny channels carved by chemical interactions. Yet even here, where water seems familiar, its role is deeper and more profound than most imagine. The crust contains far more water than we see. Water stored in microscopic pores, locked within mineral grains, and held under pressures that increase steadily as we descend. This hidden water helps regulate the temperature of the crust. It aids in the metamorphosis of rocks. It influences the structure of the crust itself, guiding how fractures form and how minerals reshape under stress. As we drift deeper, we begin to understand why the crust is such an essential gateway to Earth's hidden interior ocean. Although it appears solid, the crust is not a uniform shell. It varying thicknesses, thicker beneath continents and thinner beneath oceans, and composed of different minerals depending on age and formation history. In some places, the crust is only a few miles thick. In others, it extends more than 40 miles. But regardless of thickness, water plays a key role in its structure. It weakens some rocks, strengthens others, and affects the melting points of minerals in ways that determine where magma forms, where earthquakes may occur, and how mountains rise or fall over time. The crust also marks the first stage of a remarkable planetary process, subduction. This is the mechanism by which Earth recycles its own surface. Tectonic plates, giant slabs of crust and upper mantle, move slowly across the planet, driven by the deeper convection currents of the mantle. When an oceanic plate meets a continental plate, the oceanic plate is often forced downward, carrying with it layers of sediment, hydrated minerals, and trapped water. As the plate sinks, this water begins its long journey into the deep earth. The journey we are now following in imagination. In the upper crust, before we approach the crushing pressures below, water moves in a familiar cycle. Rain falls onto the surface, infiltrates the soil, flows into rivers and lakes, and slowly percolates downward. But not all of this water returns to the surface. Some seeps into deep fractures, descending far enough that its chemistry begins to change under increasing temperatures. It may encounter minerals that readily absorb it, locking water into their structures. It may fill cavities created by ancient volcanic activity. It may interact with rocks that reform into new minerals through metamorphism, altering the composition of the crust itself. As we continue downward, we start to feel the immense pressure of the overlying rock. Even though we are imagining this journey, we must acknowledge that the crust experiences pressures that would crush bodies or equipment long before reaching significant depths. Rock that seems solid behaves like a fluid over enough time and pressure. Minerals stretch, deform, and recrystallize. Microscopic pores shrink or close. Water that once flowed easily becomes trapped, confined to spaces so small that it may no longer behave like liquid water at all. It transitions into supercritical fluids or chemically bound hydrogen, forms of water that challenge our usual categories. It is in this zone, this transition between the near-surface world and the deeper mantle, that scientists first began to suspect that Earth might harbor far more water than previously thought. Samples taken from deep boreholes revealed minerals containing traces of water, even in rocks that had once reached depths far greater than any human drilling could hope to achieve. These minerals, pressed into the crust through tectonic motion, carried signatures of hydration from environments where water should not have existed. The deeper researchers explored, the more evidence they found of water locked away in crystal structures, waiting to be released under the right conditions. Even in the crust, which is tiny compared to the mantle, the quantity of stored water is staggering. Estimates suggest that the upper crust alone may hold a volume of water comparable to several surface oceans, though in a dispersed, hidden form. Yet, this is only the beginning. The crust is merely the threshold of Earth's deep water cycle, a cycle operating not on the scale of weather or climate, but on timescales measured in millions of years. In this cycle, water is carried downward by subducting plates, stored within minerals under immense pressure, and eventually returned to the surface through volcanic eruptions, mountain building, and tectonic uplift. As we drift deeper through the crust, the texture of the rock changes. We move from brittle layers, where earthquakes occur, to ductile layers where rock flows instead of fracturing. The boundary between these two behavior zones is not fixed. It depends on temperature, pressure, and composition. In this deeper region, water profoundly affects how rocks behave. Hydrated minerals deform more easily than dry ones. Water lowers the melting point of rocks, encouraging magma formation. In turn, magma transports water upward, feeding volcanic arcs that shape entire continents. Even though the crust seems like a thin, rigid shell, it is deeply involved in Earth's interior processes. Here we also encounter the first signs of metamorphic reactions, a set of transformations triggered by increasing temperature and pressure. Minerals that once formed at the surface become unstable in these new conditions. They break down, reorganize, and form new structures. During this process, water can be released or absorbed depending on the mineral assemblage. For instance, the mineral amphibole can hold significant amounts of water within its structure. But as it is pushed deeper and heated, it breaks down, releasing that water into the surrounding rock. That water, in turn, affects the melting behavior of nearby material, setting off a cascade of geological consequences. Through these processes, the crust becomes a laboratory in which water and rock interact continuously. Every shift in mineral structure represents a delicate balance between chemistry, temperature, and pressure. Over vast timescales, these interactions reshape the crust itself. Mountain ranges rise, erode, and rise again. Ocean basins open and close, continents drift, collide, and fracture. And all the while, water moves invisibly through this cycle, guiding and influencing the planet's evolution. As we drift deeper still, nearing the base of the crust, we reach the Mohorovičić discontinuity, often known simply as the Moho. This boundary marks the transition between crust and mantle. It is not a sudden, sharp line, but rather a zone where seismic waves change speed due to differences in composition and density. Here, the minerals become richer in iron and magnesium, transitioning from crustal rocks like granite and basalt to mantle rocks like peridotite. Temperatures rise dramatically and pressures become immense. Yet even here, water persists, not in liquid form, but in the atomic structure of minerals. The Moho marks the limit of the crust's familiar geological processes. Below this point, we enter the mantle, where water takes on forms far stranger and more tightly bound than any we have encountered so far. But before we cross this threshold, we pause to appreciate the complexity of the crust itself. Though thin compared to the mantle, the crust is essential to the deep water cycle that has sustained Earth's oceans and shaped its continents for billions of years. It is here that water begins its descent, carried downward by the immense slow motion of tectonic plates, bound into minerals that will soon be subjected to pressures and temperatures far beyond anything found on the surface. This descent is not a fall but a drift, a slow movement through geological time. The crust is a palimpsest of Earth's history, a record etched into stone. Every layer we passed held clues about ancient oceans, vanished mountains, and long-lost climates. And woven through all of it, like a hidden thread, was water, guiding, shaping, and transforming. Crossing the boundary between Earth's crust and mantle is like stepping from one world into another. Above this threshold lies the realm shaped by tectonic plates, volcanic arcs, and mountain-building forces we recognize from the surface. Below it stretches the largest region of our planet, an immense, slow-moving ocean of solid rock that behaves in ways both familiar and alien. The mantle makes up more than 80% of Earth's volume. Yet for most of human history, it remained a place of pure speculation, a hidden world far beyond direct experience. Tonight, we drift into that world, into the depths where Earth's great hidden reservoir of water truly resides. The mantle is not molten in the way many imagine. Rather than a churning sea of liquid rock, it is mostly solid, composed of dense minerals that deform slowly over time, behaving like stone in the short term, but like a very thick fluid over millions of years. Temperature rises as we descend, climbing from hundreds to thousands of degrees Celsius. Pressure increases even more dramatically, climbing to levels that would crush steel and alter the very nature of minerals themselves. Yet despite this intense environment, water persists here, not as liquid, not as steam, but as something far stranger. Water locked within the crystal lattices of minerals. This form of deep water is almost impossible to visualize from everyday experience. Imagine a mineral crystal such as wadsleyite, one of the dominant minerals of the mantle transition zone. Its atomic structure contains tiny sites where hydrogen atoms can fit, binding themselves to oxygen in a way that allows the mineral to store water, sometimes as much as 3% of its weight. This might seem small, but when you consider that the mantle transition zone is thousands of kilometers across, even a small percentage translates into an astonishing volume of water. The entire region could hold several times more water than all of Earth's oceans combined, hidden not in caverns or lakes, but as a quiet, fundamental part of the planet's structure. To understand how water ends up trapped in these deep minerals, we must follow the slow descent of tectonic plates, a process we glimpsed in Chapter 1, but will now examine more closely. Subduction drags water from the surface down into the mantle. At first, this water is carried by hydrated minerals in the crust and upper mantle of the descending plate. Minerals such as amphibole, mica, and serpentine. These minerals can hold significant amounts of water within their structures. As the plate sinks deeper and encounters higher temperatures and pressures, these minerals transform, releasing water into the surrounding rock. But the water does not simply rise back toward the surface. Instead, it is absorbed by minerals stable at greater depths. Minerals like wadsleyite and ringwoodite. The moment scientists discovered that ringwoodite can hold vast amounts of water was a turning point in our understanding of Earth's interior. For decades, theorists had suspected that the mantle could store significant water, but direct proof remained elusive. That changed in 2014, when researchers analyzed a tiny fragment of diamond brought to the surface by a volcanic eruption. Inside the diamond was a microscopic inclusion of ringwoodite, a sample from the mantle transition zone, and inside that ringwoodite was water. This discovery confirmed that Earth's deep interior was far wetter than previously believed, revealing a hidden ocean that may have shaped the planet's evolution since the earliest stages of its history. As we drift deeper into this region, known as the mantle transition zone, we encounter its two defining minerals, wadsleyite and ringwoodite. Wadsleyite dominates at depths between roughly 410 and 520 kilometers. Ringwoodite dominates from about 520 to 660 kilometers. Both are polymorphs of olivine, a mineral abundant in the upper mantle. But under the crushing pressures found here, the atomic structure of olivine reorganizes, becoming more compact and altering the mineral's properties in profound ways. One of these changes is the ability to store water. These minerals can incorporate hydrogen atoms into their crystal structures far more readily than olivine can. This makes the transition zone a vast sponge for water, able to hold multiple ocean masses within its crystalline network. Water bound in these minerals is not mobile in the way surface water is. It cannot flow or evaporate. It cannot freeze or boil. The enormous pressures keep it locked in place, part of the very architecture of the mineral. Yet this bound water still influences the physical and chemical behavior of the mantle. It can lower melting points, alter viscosity, and regulate how heat moves through the deep earth. Even in such small concentrations, measured in fractions of a percent, water has an outsized effect on how rocks behave under extreme conditions. This is why mantle minerals that contain water deform more easily than dry ones. Water enhances plasticity, making it easier for the mantle to convect and flow over long periods. Without this hidden water, Earth's mantle would be stiffer and slower, and the tectonic processes that shape the surface might operate very differently. In the transition zone, we begin to grasp the scale of Earth's interior water reservoir. This region alone could store more water than all surface oceans combined, far more than the crust or the upper mantle can hold. And because plate tectonics continually transports water downward over geological timescales, the transition zone acts as a deep, stabilizing reservoir for the planet's water cycle. If Earth did not have this capacity to store water in its interior, surface oceans might have been larger or smaller at various points in history, potentially affecting the emergence and persistence of life. The mantle's ability to store water may be one reason Earth has remained habitable for billions of years. Yet this hidden ocean is not uniform. Some regions may be wetter than others, depending on the history of subduction in that area. Areas beneath long-lived subduction zones, such as the Pacific Ring of Fire, may be particularly rich in deep water. Meanwhile, parts of the mantle beneath ancient continental interiors may be drier. These variations can influence everything from volcanic activity to the movement of tectonic plates. For instance, areas with more water in the mantle may experience more frequent or more powerful volcanic eruptions, since water lowers the melting point of rock and increases the buoyancy of magma. Conversely, drier areas may produce less magma and have more stable crustal structures. The transition zone itself acts as a buffer in the deep water cycle. As plates subduct, they release water into this region, where it is absorbed into wadsleyite and ringwoodite. But only a portion of this water moves deeper into the lower mantle. Some gets trapped in place, effectively locked away for hundreds of millions or even billions of years. Some may eventually return to the surface through mantle plumes that bring deep material upward. The transition zone's ability to absorb or release water may play a role in large-scale geological events, such as the formation of supercontinents or global-scale volcanic episodes known as large igneous provinces. Continuing downward, we eventually approach the lower mantle, beyond 660 kilometers. Here, the minerals once again undergo transformations. Ringwoodite becomes bridgemanite and ferropericlase, the most abundant minerals in the planet. Bridgemanite, in particular, dominates the lower mantle, making up perhaps half of Earth's entire volume. But bridgemanite can hold far less water than the transition zone minerals. This means that as rocks descend from the transition zone into the lower mantle, they may release water. Some of this water could help generate melt at the boundary between the two regions. Some may rise back into the upper mantle, fueling volcanism. And some may continue downward in trace amounts, potentially influencing deep mantle processes in ways that are still poorly understood. The possibility of water cycling into the lower mantle raises fascinating questions. Could water reach the core mantle boundary? Could it influence the generation of Earth's magnetic field? Could it alter the chemistry of the deep mantle or contribute to enigmatic structures seen in seismic imaging? Scientists are only beginning to explore these possibilities. Some models suggest that water may accumulate at the base of the mantle, forming pockets of hydrated material that influence heat flow. Others propose that water may react with iron in the core, forming hydrides or altering the core's composition. While these ideas remain speculative, they illustrate how little we truly know about the deep Earth and how central water may be to its mysteries. As we drift through the lower mantle, we encounter a region where pressure increases to millions of times the atmospheric pressure at the surface. Temperatures approach several thousand degrees Celsius, yet even here, water persists in trace amounts. It may exist as hydroxyl groups in bridgemanite, as hydrogen dissolved in metals or silicates, or as compounds formed by interactions between descending slabs and ambient mantle materials. These traces, though tiny, have profound implications for the physical properties of deep mantle rocks. They may influence viscosity, electrical conductivity, and the propagation of seismic waves. Indeed, some of the anomalies detected in deep seismic studies, areas where waves travel unusually slowly or quickly, may reflect variations in water content. As we journey deeper, we must acknowledge that much of our understanding of the deep mantle comes not from direct observation, but from experiments and simulations. Scientists recreate high pressures and temperatures in laboratory settings using diamond anvil cells, laser heating, and shock compression. They use computer models to simulate atomic interactions under extreme conditions. These tools allow them to infer the behavior of water in minerals like wadsleyite, ringwoodite, and bridgemanite. While uncertainties remain, the consistency of evidence points clearly to a deep Earth enriched with hidden water. Yet water's role in the mantle is not purely chemical or physical. It is also historical. Long before Earth had stable oceans or a thick atmosphere, water played a crucial role in cooling the planet, influencing magma formation and shaping the early crust. Some theories suggest that Earth's earliest oceans may have formed in part from water released by the mantle. If true, then water locked deep within the planet today may be a remnant of Earth's primordial reservoirs, a link to the planet's earliest days. Conversely, water carried downward by subduction over hundreds of millions of years represents a more recent addition to the deep water cycle. The mantle's secret ocean, therefore, is both ancient and ever-renewed, a dynamic reserve shaped by processes spanning the entirety of Earth's 4.5 billion-year history. As we ascend within the mantle, retracing our path toward the transition zone, we recognize that the hidden ocean beneath our feet is not static. It is part of a dynamic system that shapes Earth's geology, surface environment, and long-term evolution. Although the water is locked in minerals and cannot flow like surface oceans, it moves slowly through the deep Earth. It travels with subducting slabs, with mantle convection, with rising plumes of molten rock. It exerts subtle but profound control over Earth's internal dynamics. And it does all of this silently, invisibly, without ever revealing itself directly to the surface world. The mantle's hidden ocean remains one of the greatest discoveries in modern Earth science. A revelation that challenges our understanding of what a planet is and how it works. It reminds us that beneath the familiar landscapes of continents and oceans lies a deeper, more powerful realm where water takes on forms we can scarcely imagine. It reminds us that Earth is not just a world of blue oceans and green continents, but a world of hidden depths, where water binds itself to stone and shapes the planet from within. As we rise toward the upper mantle once more, preparing to follow the slow breath of the planet in Chapter 3, we carry with us a new awareness. The oceans we know are not the whole story. The mantle's secret sea, quiet, vast, and ancient, has shaped Earth's past and will shape its future. It is the deep pulse of our planet, beating slowly through time. As we return to the upper mantle from the depths of the transition zone, we begin to sense something subtle yet profound. A rhythm, a steady, almost imperceptible exchange that has been operating since the earliest days of Earth's history. This rhythm is not like the tides of the ocean or the cycles of weather on the surface. It is far slower, measured not in days or months, but in millions of years. It is the deep water cycle, an immense and ancient circulation of water between Earth's surface and its interior. Like a breath drawn and released over geological timescales, this cycle regulates the planet's stability, temperature, and habitability in ways we are only beginning to understand. Despite the apparent rigidity of the solid Earth, nothing here is truly fixed. Every part of the planet shifts over time. Continents drift like slow rafts. Ocean basins open and close. Mountain ranges rise, erode, and rise again. Beneath all of this motion lies the vast machinery of plate tectonics, Earth's unique system of moving crustal plates driven by the convective flow of mantle material. It is through this tectonic motion that water begins its deep journey downward. And it is through volcanic activity and mantle melting that water finds its way back upward, completing a cycle as old as the planet itself. We begin our exploration of this slow planetary breath at a subduction zone, where one tectonic plate sinks beneath another. These zones are scattered across the world's oceans: Japan, the Pacific Northwest, the Andes, the Philippines, and many more, forming a ring of deep trenches and volcanic arcs known as the Ring of Fire. Here, oceanic plates, heavy with sediments and hydrated minerals, descend into the mantle. With them goes an extraordinary amount of water. Not in the form of liquid, but bound within minerals formed at low pressures and temperatures near the surface. As the descending plate encounters greater depths, pressures, and temperatures, the minerals carrying the water begin to change. Serpentine, amphibole, and chlorite, all minerals capable of holding water at shallower levels, transform into denser phases that can no longer accommodate the water in their atomic structures. As these minerals break down, they release their water into the surrounding mantle. But the released water does not remain free for long. In the overlying mantle wedge, the region above the sinking slab, minerals such as olivine, wadsleyite, and ringwoodite absorb much of this water, storing it once again within their crystalline lattices. This transfer of water from one set of minerals to another forms the first part of Earth's deep water cycle. It is a slow, quiet movement, invisible on human timescales, but relentless over millions of years. At any given moment, countless mineral grains are releasing water, while countless others are absorbing it. This exchange affects the mantle's melting behavior. Water lowers the melting point of mantle rock, allowing magma to form at temperatures lower than would otherwise be possible. This is why volcanic arcs often form above subduction zones. The water released from the descending plate helps melt the mantle wedge, generating magma that rises toward the surface and eventually feeds volcanic activity. From the perspective of geological time, subduction zones act as the inhalation of Earth's deep breath. They draw water downward from the surface, pulling it into the mantle in a continuous, gradual descent. Volcanic arcs, by contrast, represent the exhalation, the return of water to the surface through volcanic emissions. When magma rises and erupts, gases including water vapor escape into the atmosphere. This water is not newly created. It is ancient water recycled from deep within the Earth, having spent millions of years locked in mineral structures before resurfacing. But not all water returned to the surface escapes into the atmosphere. Some remains trapped in new rocks formed as magma cools. Some becomes part of hydrothermal systems that circulate near volcanic regions. Some becomes incorporated into minerals at the surface, only to be drawn downward again in future cycles of subduction. In this way, Earth maintains a long-term balance between water at the surface and water in the interior. Without this balance, our oceans might slowly dry up or overflow, drastically altering the planet's climate and habitability. Consider a mountain range like the Andes. The towering peaks we see above the surface are the result of subduction, of a descending oceanic plate carrying water into the mantle. The water released from the slab helps generate magma, which rises and contributes to the growth of the volcanic Andes. Meanwhile, the pressure of the colliding plates forces the crust upward, creating non-volcanic mountains as well. Water weakens certain rocks, allowing them to deform more easily and rise into mountain belts. Without water, the Andes might be lower, narrower, or shaped differently altogether. Similarly, consider the formation of ocean basins. Mid-ocean ridges, where tectonic plates diverge and new crust forms, are also influenced by water. As mantle material rises beneath the ridge, it decompresses and melts. Water stored in the mantle lowers the melting point of the rising rock, making it easier for magma to form. This magma then cools to create new oceanic crust. Over time, this crust will travel across the ocean basin and eventually descend into a subduction zone, returning its water to the mantle and completing the cycle. As we reflect on this slow planetary breath, we begin to appreciate how many processes on Earth depend on the deep water cycle. The distribution of volcanoes, the shape of continents, the rise and fall of mountains, the creation of new crust, the destruction of old crust, all are influenced by water. Even Earth's long-term climate is affected. Volcanic eruptions release not only water vapor, but also carbon dioxide, which plays a central role in regulating global temperature. The deep water cycle interacts with the carbon cycle through processes such as volcanic degassing, subduction of carbon-bearing sediments, and metamorphic reactions that release or absorb carbon dioxide. Without these interactions, Earth's climate might have been far less stable over geological time. Yet the deep water cycle is not perfectly steady. It can be disrupted by large-scale geological events. For example, the breakup of a supercontinent can alter patterns of subduction and volcanism, changing how much water is carried into or released from the mantle. Similarly, the formation of a supercontinent can reduce the number of active subduction zones, slowing the cycle and potentially affecting ocean volumes. These long-term geological rhythms may have contributed to major environmental shifts in Earth's history, including mass extinctions and periods of extreme climate change. Even today, scientists study the deep water cycle to understand how Earth might evolve in the future. If subduction rates change due to tectonic reorganization, if volcanic activity increases or decreases, if new continents begin to form or collide, the distribution of water between the surface and the interior could shift. Over millions of years, such shifts could influence sea levels, climate patterns, and even the composition of the atmosphere. To understand these long-term effects, we must examine the deep water cycle from a broader perspective, one that includes not only subduction and volcanism, but also the mantle's internal convection. Mantle convection is the slow movement of solid rock driven by temperature differences within the Earth. Hotter, less dense material rises, while cooler, denser material sinks. This convective motion continually stirs the mantle, mixing regions of differing composition and water content. Some of this water remains trapped for extremely long periods, while some is cycled upward or downward, depending on the dynamics of the region. Imagine rising mantle plumes, columns of hot rock that ascend from deep within the Earth. These plumes bring with them material that may have been isolated for billions of years. As the plume approaches the surface, the pressure decreases, allowing water in the minerals to influence melting behavior, Volcanic hotspots such as Hawaii or Iceland are thought to be fed by mantle plumes. Their eruptions are enriched in volatiles, including water, suggesting that even deep mantle sources contain traces of Earth's hidden water. Some plumes may tap into reservoirs at the core mantle boundary, hinting at the possibility that water or water-related compounds may exist far below the mantle transition zone. Other regions of the mantle, however, may be drier. These variations reflect the complex history of mantle convection. Some areas have received more water through subduction. Others have lost water through melt extraction. Some have remained isolated from surface processes for long periods. Studying these variations helps scientists understand how the mantle behaves and how Earth's interior has evolved. As we continue drifting through this vast, dynamic interior, we recognize that the deep water cycle is more than a simple physical process. It is a crucial part of what makes Earth unique. No other planet in the solar system appears to have an active, long-term system for recycling water between the surface and the interior. Mars once had surface oceans, but today lacks the tectonic activity needed to recycle water deep into its mantle. Venus may have lost its early water to the atmosphere, where it escaped into space. Earth alone maintains a stable balance, replenishing its oceans over time and keeping its climate within the narrow range needed for life. The deep water cycle also allows Earth to continually renew its surface. Old crust is subducted and recycled. New crust emerges at mid-ocean ridges. Mountain ranges form and erode. Without this recycling process, Earth's surface might gradually become stagnant, with no new crust forming and no old crust disappearing. Plate tectonics itself is influenced by water. Some scientists believe that water trapped in the mantle lowers the viscosity enough to allow plates to move. If Earth's interior were completely dry, plate tectonics might not be possible. Without plate tectonics, Earth's oceans might have evaporated long ago, and life might never have emerged. As we explore these deep processes, we begin to see Earth not as a static sphere of rock, but as a living, breathing world. A planet whose interior cycles mirror the complexity of life itself. The slow breath of the planet, drawing water down and releasing it back to the surface, is part of a system that maintains Earth's long-term stability. It is a silent, patient rhythm, operating far beneath our awareness, shaping the planet in ways we rarely consider. Now, as we drift slowly upward once again, preparing to return toward the surface in Chapter 4, we carry with us the understanding of how deeply interconnected Earth's interior and surface truly are. The water we see in oceans, rivers, and lakes is only the visible part of a much larger story. Beneath our feet lies a hidden network of reservoirs, pathways, and cycles that regulate the entire planet. The slow breath of the Earth continues, drawing water inward and pushing it outward, shaping continents, fueling volcanoes, building and destroying landscapes, and sustaining the oceans that make life possible. It is a quiet, persistent rhythm, one that will continue long after our lifetimes, long after continents have drifted to new positions, long after new mountains have risen where oceans once lay. As we begin our slow ascent from the deep mantle toward the surface, the world around us shifts once again. The crushing pressures ease, though they remain immense. Temperatures gradually decline, though they stay far beyond anything found on the surface. The minerals that once absorbed water in the transition zone begin to give way to those that cannot hold it as tightly. And through these small, cumulative changes, something remarkable begins to happen. Water that has been hidden within Earth for millions, even billions of years, starts its long journey back to the surface. This return is not dramatic. It does not occur in sudden floods or roaring torrents. Instead, it unfolds through slow, patient processes that operate over vast geological timescales. Much of the water is still locked in minerals, trapped in the crystal lattices where it has resided since the days when continents were arranged in patterns unrecognizable today. But as mantle material rises, as part of the convection currents that govern the deep Earth, these minerals begin to encounter lower pressures and temperatures, conditions that gradually destabilize them. They change their atomic structure, releasing the water they once held. This returning water does not appear as liquid. It emerges as hydroxyl groups, as hydrogen atoms bonding with oxygen in the surrounding mineral matrix, as tiny pockets of supercritical fluid, and eventually as volatile components in rising magma. It becomes part of a chemical soup that subtly alters the properties of the mantle material it inhabits. And in doing so, it begins to influence processes far above, where its presence will affect volcanic eruptions, crust formation, and even the atmosphere that envelops the planet. Our journey upward brings us into regions where the mantle begins to rise more quickly. Regions where convection currents transfer heat and material from deeper layers toward the surface. This rising mantle encounters decreasing pressures, lowering the melting point of the surrounding rock. When water is present, the melting point drops even further. This phenomenon helps generate magma in subduction zones and in hotspots around the world, creating the volcanic systems that return deep water to the surface. Volcanoes are the most spectacular expression of this rising water. They are the pathways through which ancient water, trapped for eons deep beneath the surface, finally escapes into the atmosphere. When magma reaches the surface and erupts, it releases gases that include water vapor, carbon dioxide, sulfur dioxide, and many other volatile compounds. The water vapor released during volcanic eruptions is not the same water that fills our lakes and rivers. It is water that has traveled through the mantle, been locked in minerals, undergone transformations under enormous pressure, and been carried upward within rising magma. The water found in volcanic eruptions offers clues about its deep origins. By analyzing the composition of volcanic gases and the isotopic signatures of erupted materials, scientists can trace the pathways of water from the surface to the deep interior and back again. These analyses reveal that some volcanic water is ancient, dating back to early Earth, possibly even derived from materials that formed the planet itself. Other components of volcanic water originate from surface oceans, carried downward by subduction. This mix of ancient and recycled water underscores the complexity of Earth's deep water cycle. As we continue our ascent, we pass through the upper mantle, where the influence of water becomes even more pronounced. Water affects the viscosity of mantle rocks, making them flow more easily. This flow influences the movement of tectonic plates, helping them glide across the surface. Without water, the mantle would be stiffer. Plates would move more slowly, and Earth's surface might lack the dynamic features we take for granted. Mountains, ocean trenches, volcanic arcs, and the shifting mosaic of continents. Water also influences the formation of new crust. At mid-ocean ridges, where tectonic plates diverge and mantle material rises, water helps generate the magma that forms new oceanic crust. As hot mantle rock rises and begins to melt, water lowers its melting point and contributes to the formation of basaltic magma. As this magma erupts onto the ocean floor, it cools and solidifies, forming new crust that gradually spreads outward across ocean basins. Over millions of years, this process contributes to the renewal of Earth's surface and the long-term regulation of ocean volumes. Even though these processes are slow, their cumulative effects are profound. Without water in the mantle, Earth's crust would be thicker and more rigid. Volcanoes might be fewer and less active. Ocean basins might evolve differently, with implications for climate stability and sea level. The presence of water deep within the Earth, therefore, is not merely a curiosity. It is essential to the planet's long-term evolution. As we rise further toward the surface, we encounter regions of partial melting known as magma chambers. These chambers are not vast, open caverns filled with molten rock, as they are sometimes imagined. Instead, they resemble networks of molten pockets and crystalline mush that exist within the surrounding rock. Water plays a critical role in the formation and evolution of these magma reservoirs. It reduces the viscosity of magma, allowing it to flow more easily. It also increases the volume of gases within the magma, contributing to the explosive potential of some eruptions. In some volcanic systems, water-rich magma produces spectacular eruptions that send ash, gas, and lava into the atmosphere. In others, the presence of water leads to quieter eruptions, creating lava flows and building shield volcanoes. The style of eruption depends on many factors: composition of the magma, temperature, pressure, and the amount of water and other volatiles present. The diversity of volcanic behavior across the planet reflects the diversity of conditions within Earth's mantle and crust. The water released during volcanic eruptions can take many paths. Some enters the atmosphere, where it contributes to cloud formation and precipitation. Some condenses in hydrothermal systems, feeding hot springs and geysers. Some reacts with rocks near the surface, contributing to the formation of minerals, such as clays. And some becomes part of the hydrological cycle, eventually entering rivers, lakes, and oceans. Over millions of years, the cumulative effect of volcanic degassing helps maintain Earth's surface water inventory. Yet even as volcanic eruptions return water to the surface, subduction zones continue to draw water downward. The balance between these two processes, the return of water by volcanism and the descent of water by subduction, determines the long-term distribution of water between Earth's interior and its surface. Geological evidence suggests that this balance has remained relatively stable over billions of years. If it had not, Earth might possess far more or far less surface water today. As we approach the crust once more, we enter a region where rising magma begins to cool. Water dissolved in the magma starts to escape as pressure decreases. Some escapes as gas, while some remains trapped in solidifying minerals. These minerals may later be uplifted by tectonic forces, exposing them at the surface, where erosion, weathering, and other processes release their water content over time. The return of water to the surface is not simply an exhalation of the deep Earth. It is a process that sustains many of the surface environments we depend on. Hydrothermal systems near volcanoes, for example, are fueled by water released from rising magma. These systems support unique ecosystems, influence mineral deposits, and shape landscapes through erosion and chemical alteration. Geothermal energy, harnessed by humans for heating and electricity, is also a product of water circulating through heated rocks near the surface. As we drift through these shallow depths, we begin to appreciate how interconnected the deep Earth and the surface environment truly are. The water that emerges from volcanic systems may eventually fall as rain, flow into rivers, freeze in glaciers, or become part of living organisms. It may enter the oceans, contribute to the water cycle, and, over millions of years, be drawn downward again through subduction. In this way, the hidden waters of the deep Earth continually replenish and support the surface environment. Now, as we rise through the final layers of the crust and approach the surface, we return to the world of light, air, and familiar landscapes. But we do so with a deeper understanding of the hidden processes that shape our planet. Beneath every continent and ocean lies a vast reservoir of water locked within minerals, cycling slowly through the Earth's interior. This hidden water influences everything from volcanic eruptions to plate tectonics, mountain formation, climate regulation, and the long-term stability of Earth's oceans. The water that emerges at the surface today may have begun its journey hundreds of millions of years ago. It may have been part of ancient oceans, long before the first plants appeared on land. It may have been trapped in mantle minerals during the formation of the earliest continents. It may have traveled deep into the Earth's interior, endured crushing pressures and extreme temperatures, and emerged anew through volcanic breath. As we step onto the surface once more, our journey complete, we carry with us a new perspective on the world beneath our feet. Earth is not a dry, static sphere of rock, but a dynamic planet driven by hidden forces and ancient cycles. Its deep water reservoirs, locked within minerals and churned by tectonic motion, are as vital to the planet's evolution as the oceans we see on the surface. This is the quiet truth of Earth's hidden waters. They shape continents, fuel volcanoes, regulate climate, and sustain the oceans that make life possible. They are part of a planetary system more ancient and more intricate than anything we experience directly. And though they remain invisible, locked away in stone, their presence echoes through every landscape, every ocean wave, every drop of rain. Now, as the surface world surrounds us again, with its wind, its oceans, and its familiar rhythms, we know that beneath it lies a deeper rhythm, slow, patient, and timeless. The return of Earth's hidden water is not an ending, but part of a cycle that will continue long after our lifetimes, shaping the planet in silence,